Greetings, fellow mathematicians. We're going to take a look at another improper integral, and this one involves quite a lot. Integration by parts, L'Hopital's rule, and a basic graph. So let's get started. We'll take our time. This is the first type of improper integral. You can see the infinity in the integral sign. We know what to do. We're going to replace the infinity with a variable t, and then take a limit as t approaches infinity. So step one, let's set this up. A limit as t approaches infinity. And then we evaluate the integral from 0 to t of x times e to the negative x dx. All right, first step from here, always evaluate your integral and then take a limit. So let's go ahead and do that. We're going to evaluate our limit from 0 to t of x times e to the negative x. And this is going to involve integration by parts. So let's go ahead and find the antiderivative first, and then we'll apply the limits. All right, and if we integrate by parts, we'll choose our u as x, and our dv as everything else, e to the negative x dx. Calculate your du. We'll get 1 dx, or just dx. And when you integrate dv, you can apply the 1 over a shortcut. Here, the value of a is -1, so we get our antiderivative as negative e to the negative x. Now you can apply your integration by parts formula. You get uv, so negative x times e to the negative x, and then minus the integral of v du. Notice v contains a negative, so the minus in the integration by parts formula, I can write that as plus. Now the integral of v du, the integral of e to the negative x dx. And that integral we actually already calculated here. We just get a negative. So our antiderivative, negative x e to the negative x, we get another minus e to the negative x plus c. All right, just to make some of the work from here a little bit easier, let me go ahead and factor out negative e to the negative x. So I can write my antiderivative like that. All right, so that is your antiderivative. Now we just need to apply the limits here. With your antiderivative and a definite integral, you don't need the plus c. So we're going to evaluate negative x plus 1 times e to the negative x from x equals 0 to x equals t. And we just need to plug in here. Just be careful with your signs. If you plug in, looks like we're going to get negative, and then in parentheses, t plus 1 times e to the negative t. We subtract with the fundamental theorem of calculus, but there's a negative. Subtracting a negative becomes plus. And our last term here, by plugging in x is 0, e to the 0 is 1. So it looks like we can write this as negative t plus 1 times e to the negative t plus 1. And that is the value for your integral. And now we can evaluate the limit. So let's go ahead and plug that in right up here. We have the limit as t approaches infinity. And then we're taking the limit of the answer we got from evaluating the integral. Negative t plus 1 times e to the negative t plus 1. All right. Now at this point, we need to rely on some basics about limits, which might have been forgotten. You last used L'Hopital's rule probably in the middle towards the end of your Calc 1 course, and it comes back now. So we have a very brief refresher here. Let's see maybe why we need L'Hopital's rule here. So we're going to be taking a limit as t approaches infinity. And notice here we have two terms, t plus 1 and e to the negative t. Now, as t approaches infinity, t plus 1, that's going to approach infinity. But your exponential term, e to the negative t, you can see from your basic graph of e to the negative x, as you approach infinity, the exponential function approaches 0. So what we have here is an indeterminate form as t approaches infinity, but it's of the type infinity times 0. Now, L'Hopital's rule, as you learned it in Calc 1, applies to indeterminate forms of type 0 over 0 or infinity over infinity. So we're going to have to try to rewrite this in order to apply L'Hopital's rule. We're going to go ahead and get to that right now. Before we apply L'Hopital's rule, let's just make sure you realize what we're applying it to. We're trying to evaluate the limit of this term, the limit of t plus 1 times e to the negative t as t approaches infinity. Now, our limit here does give us an indeterminate form, as we mentioned, but it's an indeterminate form of type infinity times 0. L'Hopital's rule applies to 0 over 0 or infinity over infinity as your indeterminate forms. So we're going to have to rewrite this function, but fortunately, this is really easy. We can take e to the negative t, which has a negative exponent, and we can just flip that. This is the same thing as 1 over e to the t, and that's going to make rewriting this as a fraction, a function divided by another, that's going to make that very simple. So we are not applying L'Hopital's rule yet. We're just taking a limit of the function in a rewritten form. Now we're rewriting it as t plus 1 divided by e to the t. Always check that you get an indeterminate form before you apply L'Hopital's rule. I always look for that in my Calc 2 course with my students. So let's check as t approaches infinity, the numerator approaches infinity, and the exponential function e to the t, notice there's no negative there. The exponential function, that grows and approaches infinity as you go very far to the right. So we do get an indeterminate form of type infinity over infinity. That means we can apply L'Hopital's rule. The limit stays the same. And now we differentiate numerator and denominator individually. Do not apply the quotient rule. So we differentiate the numerator with respect to t. You'll get 1. Differentiate the denominator e to the t, it's itself. And now we don't have a limit involving an indeterminate form. Notice your limit here, your numerator staying as 1, but your denominator is getting exponentially big. 1 over a big number is small. So this limit here approaches 0. And that is most of the work for this question. We were using L'Hopital's rule to evaluate this limit up here. And what we see is this whole term, as t approaches infinity, that approaches 0. Now, the whole limit is not 0, just this term. The whole limit here approaches 1. That limit exists, so this means our improper integral is convergent. And that completes evaluating the improper integral. It's always nice to tie the limits here and definition of the improper integral in terms of its basic idea of integrals represent area. We can always tie that into what this number means in the case of your improper integral being convergent. The graph here of x times e to the negative x is a little complicated. but it's not too bad. There's a horizontal asymptote, and that's a very rough shape of x times e to the negative x. Now our integral here goes from 0 to infinity, so the entire area beneath that graph over the entire x-axis all the way to infinity, we can conclude that that area is 1. And that's a nice way to interpret what this improper integral means. Hopefully you enjoyed the content. Make sure you kind of keep on top of the basics that we're throwing in. Those are often neglected in typical calculus courses. I always like to make sure I mention them to my students to make them successful. Hopefully you're enjoying the video and learning a lot. Support the channel, like and subscribe.